Hi, this is a poster session for the student poster contest. Number 1124 1075 64 11 24. Investigation of fast frequency contingency reserve with large scale renewable integration. My name is Indira Alcaide from the University of Queensland. The requirement of fast frequency contingency reserve of a battery is crucial because an overestimated reserve increases the grid operation cost, while an underestimated reserve is a hazard for the grid. Currently, grid operators employ a huge amount of time and resources for assessing this reserve. A generalized method to determine the contingency reserve of a battery from a broader and simpler approach is required. We propose a method depicted in the left-hand side. First, we decide a potential contingency, which is usually an outage of a large generation unit. Then we select one or more power reserves to be tested and a set of trigger and fully activated times. These are related to the delays and ramp rates of batteries. Then we perform dynamic simulation of every single combination of the aforementioned parameters. We plot the results of frequency nadir power reserve versus the set of trigger and fully activated times. We can organize the results of the contingency reserve into sufficient when the frequency nadir is very close to the frequency load shedding limit, non-sufficient when the frequency nadir is lower, and overestimated when the frequency nadir is larger than the frequency load shedding limit. This can be validated using a dynamic model of a battery. So results of an average realistic grid scenario is shown in the right-hand side, while we trip a 750 megawatt generation. So we test three different reserves, in this case, 170 megawatt, 200 megawatt, and 250 megawatt, with a wide range of trigger and fully activated times. So we can see how the frequency nadir is organized, and then the power reserve is also identified in order to have the contingency reserve into three different variables: power, reserve, trigger time, and fully activated times. We pick one of the pair of time response capabilities from the graph in order to validate by using a generic best model with droop control. So with a battery of trigger time or delay of 50 milliseconds and a fully activated time of 1.5 seconds, the star market of the previous slide, we can see two main things. The first one, a negative load can accurately represent the frequency response from the time of the contingency until the frequency nadir is achieved. And number two, the non-sufficient, sufficient, and underestimated contingency identified by the method can be very accurate according to a best model with droop control. So our conclusions are that the presented method identifies the fast frequency contingency reserve by using a negative load, which is a broader and simpler approach. And we organize the contingency reserve not only in terms of megawatt, but in terms of power reserve, trigger time, and fully activated time. So the validation was done via realistic grid under a large generation outage and a generic battery storage model. Future work will include determination of contingency reserve of wind and solar PV for FFR. Thank you.